Hey, Wade.
Hey, Carly. Today we're going to talk about my favorite formula in all of data science, a formula known as Bayes' rule.
Can you explain Bayes' rule?
Yeah, Bayes' rule is what I think of as the PhD formula because you can express it as the probability of some hypothesis given data is equal to, and so this is a conditional probability.
Yeah, this looks exactly like the conditional probability notation. I did basically the same thing, except I said the probability of event A given event B.
So Carly solves this problem using a contingency table, but I hate tables. I want a formula that I can always plug data into and always get an answer at the end as long as I have all the data. So Bayes' rule, given a prior probability, so this is what we consider in computer science, we often call these priors, that we already know this beforehand.
Okay.
So this is our prior information, and this is a hypothesis. So given a hypothesis, given some prior data, I remember this formula by how I first learned it, which is when I was working on my PhD, I might have got some little crazy sometimes, and my PhD got garbled up a little bit, and after a crazy night, I was thinking of P of D given H. So got my letters confused a little bit. But then once I went to sleep and before I defended my PhD, everything got straightened up after a little bit of rest.
PhDs are a crazy journey.
Yes. So this formula basically gives us a way to rewrite a conditional probability in terms of the opposite ordering. So given that we want to solve P of given H given D, we can solve this in terms of P of D given H times P of H over P of D.
Cool. Should we look at an example to see Bayes' rule in action?
Yeah, so I know that one of your favorite examples is the Taylor Swift example. Can you give me the details?
Let's do that and see. We should get the same result as when I solved it with the table. So the details are, this was a genetic test. We were trying to test to see if people were related to Taylor Swift, and they told us that 1% of the population is related to Taylor.
So every time Carly mentions an important piece of statistics, I'm going to write it in formula form.
Great.
So Carly said the probability of being related to Taylor is 1 out of 100.
Yes, exactly. And then this test, this genetic test, it wasn't 100% accurate, but there was a 99% chance that given you are related, you would get a positive result. So that's good.
So the probability of getting a positive result given you are related was, what did you say that was?
That was 99%.
So 99 out of 100.
Maybe as good as we're going to get. And then the test also, we said it wasn't perfect, so you could get something called a false positive. There was a 6% chance of getting a false positive, which basically means you get a positive result given that you're not related. And that was 6%.
6 over 100.
Oh, and Wade, you wrote a little 7 there. What does that mean?
Yeah, so this is the way that a lot of data scientists, especially if they have a computer science background, will write the negation. So I want to know not related. So this is, if I think of this generically in terms of event A, and as I write down probabilities, you're going to see me write, if I have an event A, this is normally just event A. If I want to know about A not occurring, I would write not A. But Carly, you use a different syntax.
Yeah,
statistics.
to represent the same thing, I would call this the complement of A, or the opposite of A. And I use the A with a little C. So means the same thing, slightly different notation. And are there any other ways to write not or negation?
Yeah, there's one other way. And in computer science, you'll often see people write negation as having a bar or a line over the top of a variable.
Got it.
So all 3 of these all signify that A, not A.
Yes.
So A did not occur.
Yes.
So was this all of the test data we have for Taylor?
That was everything I knew for Taylor.
Okay, so what I want to solve is I want to solve the probability of someone being related to Taylor Swift, hopefully me.
Yeah.
Given they just got a positive test result from the lab.
And you did get a positive result.
I did. So I'm hopefully related, and I want to know what the probability is that I'm actually related given that positive test result.
Perfect.
So here I have a formula, and I can see, do I have this formula itself? And it's like, I don't have that in any of my given data. I don't have related given positive, but I do have positive given related. So I can use Bayes' rule to help me solve this problem. So I'm going to go ahead, basically every time I see an H, that's related. Every time I see a D, that's a plus sign. So probability of related given a positive test result is the probability of a positive test result given they're related times the probability of the H, which we said was related, divided by the probability of a positive result. So let's go ahead and fill in the information that we have.
Perfect.
So the first piece of information we have is we have the probability of related given positive. We've got that right here. So that's 99 over 100 times the probability of related. We've got that right here. So that's 1 over 100 divided by the probability of plus. So we don't have the probability of plus anywhere in our given data.
But I think we can find it, right?
Yeah, so how would you go about doing that?
So I know for sure I want to use these because this is the probability of positive given related, and then this is the probability of positive given not related. But I probably should combine kind of all of these things to find that.
Yeah, so when we want the probability of an event occurring, we just need to simply say, what's the probability of the event occurring given some data? So the probability of event occurring given that we're related times all the population who's related to Taylor Swift.
Got it.
And then we add to that all of the other possibilities to make sure that we include every single positive result. Luckily, we only have related and not related. So we only need two different things to combine to get the entire universe of everyone who got the positive test. So this is a positive test given that we're related times everyone who is related, plus the probability of a positive test result given that we're not related times everyone who is not related. So now we can just go ahead and fill in these four individual pieces. So the probability of positive result given related is right here in our formula. So this is 99 out of 100. Probability of being related to Taylor Swift, well, that's 1 out of 100. Plus the probability of positive result given not related, well, that's 6 out of 100. And Carly, probability of not related, we don't have that.
We don't have that, but we do have the probability of being related. And there's only two options, right? You're either related or you're not. So if 1 out of 100 people are related, then 99 out of 100 are not related, right?
Yeah, so a complement is always going to be 1 minus the actual event occurring.
The actual event, yep.
So we know that the complement is 1 minus 1 over 100, or 99 out of 100 people are not related to Taylor.
Right, so basically we have related, and from that we can find the probability of that not occurring.
So times 99 out of 100. So if I go ahead and solve this probability of a positive test result, well, that's 99 out of 100 squared plus 6 times 99 out of 100 squared. And that's going to be 7 times 99 over 100 squared. So I can go ahead and plug that in up here to the probability of positive. So that's going to go right here. That's going to be 7 times 99 over 100 squared. And now I can rewrite this all as multiplication, because when you divide by something, you're multiplying by the inverse. So rewriting this entire formula, I have 99 over 100 times 1 over 100 times 100 squared over 7 times 99. And this works out really beautifully because
it looks like a bunch of things cancel.
Yeah, I've got 100 squared canceling out here, and I've got
99 canceling out.
99 canceling out in the bottom, and I get 1 out of 7. So this is about 14%.
And if we remember from when I did this with the conditional probability table, I got the exact same thing, 2 out of 14, which reduces to 1 over 7. And again, we see that Wade's probability, given that he got this positive test result of actually being related, is pretty low.
So this is why I love probability, and why this is so interesting to learn about this from two people who have two very different viewpoints.
Exactly. And either method that you use, if you use the contingency table versus Bayes' rule, you'll get the same answer. And both of them require different types of work. Like in Bayes' rule, we had to figure out this probability of getting a positive. But in the contingency table, we had to go and draw out that whole contingency table. So they both have their pluses and minuses. And We hope that you guys enjoy solving these problems just like we do.
And you can use any method you want, whatever method you choose. And you're going to see I'm naturally going to go to this method. So you'll see me use this method, and you're going to see Carly use the table. And as we go through different examples, you'll see both of our perspectives as we dive into these problems.
Yes.
See you then.